Dostoevsky. I'm the chair of the Systematic Review and Meta-Analysis SIG as part of AERA. Couple of quick announcements first. We've got a program together for the 2024 AERA convention. Just wanted to give a big shout out to Carlton Fong, who looks like he just logged on there, and Derek Rogers, our program co-chairs. Thank you to them for organizing the program, and thank you as well to everyone who reviewed proposals and submitted proposals. The program looks really great. It's going to be our usual mix of papers on new methodology, papers on applications of systematic review in education, and there's some really exciting work. So keep an eye out for that. More to come about the program soon. Let's see. I don't think we have anything else. So we'll proceed with our main event then. I'm really pleased to introduce František Bartoš, who is a PhD candidate at the University of Amsterdam. He's been working now for several years on a really intriguing direction, I think, in bringing in ideas from Bayesian model averaging into the space of meta-analysis as well as models for selective reporting. And he's going to be presenting some of that work here this morning. And we'll follow our usual rules of if you feel free to type your questions into the chat during the presentation, and we will monitor the chat and kind of collate the questions. Interrupt if need be. Otherwise, should be plenty of time for discussion after the presentation. So, František, welcome, and please take it away.
Hey, thank you, and thank you for having me here. So, I'll present a bit of the work that I've done with my colleagues, Maximilian Meyer, Eric Jan Wagemakers, and Tom Stanley. And the title of the talk is RoBMA Meta-regression, a model averaging across moderation analysis in the presence of publication bias. And in the talk, I will try to cover multiple things. So the good thing is that I'm at the seminar with meta-analysis. I don't have to explain what the meta-analysis is. So I will consider that being covered. Then I will slightly touch upon publication bias, just to remind us why we care about it and to have some background for the later slides. And I will slightly touch upon robust Bayesian meta-analysis to get the concepts of Bayesian model averaging and how RoBMA works. And then I will finally get into the meta-regression and what are some additional challenges when you want to do Bayesian model average meta-regression. So if we dive right in, then just a small reminder what publication bias is or how you can define it. You can think about that most large studies are probably likely to get published regardless of the results because they are interesting enough to pass the publication filter. If the studies are smaller, then there might be some selection, depend whether they provide compelling results. And if the studies are very small, then they might be less likely to publish unless they are still significant. So this would be some very high-level summary of publication bias. And before I get further, maybe I will just quickly show some distribution of test statistics or how test statistics behave when you have studies of different power, to just prime you for some next slides. And as imagine you repeat a test, for example, a z-test multiple times, and you have a test with 30% power, and you look at the test statistics. And if you collect the absolute z values of the test statistics, then 30% of those will be statistically significant because there's the power of your test. And this will be the distribution. And if you increase the power of the test, then the test statistics will be moving more and more to the right side of the distribution. And for example, 80% majority of the test results will be significant. And then eventually, if you have test statistics with mixture of different powers, you will observe some smooth distribution. So the only thing that matters here is that the distribution should be smooth. And that's when all the studies are reported, of course. But when you look at the test statistics from published studies from PubMed, this is 1 million test statistics, you see that the distribution is nothing in the terms of smoothness. And there are 2 peaks that maybe just by accident are at a statistical significance level. So this would be, I would say, an indication of publication bias, and that might be a problem when we are trying to look at the published literature. And importantly, this is not just a problem for the published literature itself, but for meta-analyses, because what meta-analyses try to do, they are trying to summarize the published literature and to get some overview of some underlying effects. So for example, if you look at a very nice study that I will use for illustration throughout the manuscript of comparison of meta-analysis and registered replication reports by Quarman et al. What they did, they found out 50 meta-analyses from psychology. And then for each of those large meta-analyses, they found very large registered replication report of a corresponding experiment that was representative of the meta-analysis. And under some assumptions, you can think that the registered replication report should be the true estimate of the effect because it was pre-registered and it was reported regardless of the outcomes across multiple labs. So it should be very high quality estimates. And then the published meta-analyses are just summaries of the literature, and they might be affected by publication bias. And ideally, if there was no publication bias, then the meta-analytic estimates should correspond to the registered replication report's estimates. So if we quickly look at this figure, there's 15 meta-analytic estimates from the different meta-analyses. These are just random effect estimates, and they are in red. So you, for example, see that the Oppenheimer et al. Meta-analysis has effect size of around 0.45 or 0.15. And when I click now, you can see the corresponding registered replication report estimates. So these are in blue, and you can see that basically all of them are shrunken towards 0. And some of them are shrunken just a bit. Some of them, for example, the Tversky and Kahneman study has basically the same estimate. And then many of those, especially at the bottom, basically end up at 0. So this would be, I would say, a good indication that publication bias also affects meta-analyses. And this problem of publication bias is known for a couple of decades. So I'm not the first one talking about how to adjust for publication bias. And in fact, there have been plentiful of papers and a lot of methods proposed to deal with the publication bias in meta-analyses. And I like to split the methods into 2 categories. And one of them would be models that adjust relation between effect size and standard errors. So you can categorize, for example, trim and fill here, pet piece, endogenous kink. And then the other would be selection models on p-values. And the 3PSM, 4PSM models is probably the most well-known. Then AK1, AK2, I would say, are basic rebranding of the selection models. And then you have some other different psychological methods. They are working on very similar, on this very similar basis. So what I will do, I will just quickly say something about pet piece and 3PSM that will set up the rest of the methods that work in RoBMA, and also what we do and what are the limitations of those methods. So in case you haven't heard of pet piece, it's basically a conditional meta-regression estimator. So it means that the method tries to correct for the relationship between effect sizes and either standard errors or standard errors squared. And it's conditional because it means you have to select one of those 2 methods. And the intuition why this method works is you can look at the distribution of estimates and standard errors. And if there is no relationship between effect size and standard errors, then they should look more like, if you see my mouse, it should look more like a cone rather than just a bracket. But I don't know how to create triangles in PowerPoint, so it's just a square when I'm creating the censoring. But there should be, if you fit the line through the standard errors, it should be just straight line if there is no publication bias. And then you can use this estimate as when the straight line, the regression line intersects with 0, then zero meta-analytic estimate. Basically, what would be the effect size if there is, when there is no standard error. However, if there is some selection, then the distribution, then there will be much larger amount of small studies that have large effect sizes because they were interesting enough to be published. And if you fit and if you just take a mean of all those studies, then you will overestimate the effect estimate. And then PET and PEACE, those two models try to correct rate, and PET just fits a regression of standard errors on effect sizes. And according to the paper, you should select PET if you don't find a significant effect on alpha 0.10. And if you find a significant effect with PET, then you should fit a PEACE, which should provide much better approximation to this distribution of standard error and effect sizes. So you basically have to do a choice between those two estimates of those methods. And one of the problems is that you are choosing between two different models based on significance, and sometimes the decision might be very close. And the models can give very different results based on your statistical test. Then the second model that I would just briefly touch upon are selection models, and they just expand the usual meta-analysis, either fixed or random effects meta-analysis, by adding publication best weights omega. And you can think about it as you specify a weight function, which is on the left side, and the weight function is joined with the likelihood, and you estimate them simultaneously, and it discounts your likelihood at places where there is lower publication probability, and that allows you to fit the model to the data. And for example, here there's 3 steps at the weight function. So omega-3 would be set to 1, which would be the statistically significant p-values, and you would have selection on marginal significance. That's here is somewhere between, it's around 0.5, let's say. And then you have omega-1 that you also estimate it would be 0.2. And that when you join with the likelihood, which the normal likelihood be just F, and the weighted likelihood, you see you have these peaks. That should remind you of the distribution of the statistics that we, for example, observed in the PubMed. So that would be as reason why you might decide to use selection models. And when you do selection models, you can you have also multiple choices you can do. You have different weight functions you can specify. And even if you just decide to use step weight functions, you can put multiple weights, you can put multiple steps, etc. So there's another plethora of options. And if we just quickly look how these methods perform on the comparison of meta-analyses and research reports, you see that on some meta-analyses, the red circle, which is PET PEACE, and the triangle, which is 3PSM, performs exactly as the meta-analysis, which is and the research report, which is good in this case. In other cases, it seems that PET PEACE underestimates a lot, but the 3PSM adjusts a bit the unadjusted estimate. But in other cases, PET PEACE performs better than the selection models and original random effects. So just to summarize the limitation of those methods before I move forward, is that they usually require the researcher to decide which unmodeled methods they should use. And it's kind of not obvious which one method is correct for different scenario. And then the decision makes a lot of difference for the results. And the methods also can quantify evidence against publication bias, because non-significant p-value doesn't indicate evidence of absence, only absence of evidence. And they often fail under high between study heterogeneity. And if there are small sample sizes, they usually perform very badly, and they have convergence issues. For example, 3PSM is very hard to fit when you have only a few studies, and if you don't have any studies at different p-value intervals. So we try to solve many of those issues with originally with RoBMA, which stands for robust Bayesian meta-analysis. And we use, in overview, we use Bayesian model averaging to base inference of multiple models simultaneously. So you don't have to choose any of those different models, but you estimate all of them. And then you base the results accordingly how well they predict data. I will talk a bit more about this later. It uses Bayes factors that allows you to quantify evidence either in favor or against the presence or absence of either effect, heterogeneity, or publication bias. So not only you can provide evidence, but evidence for, but also evidence against. Because we are in Bayesian setting, we use prior distributions on all parameters, and that helps us regress the estimates. And that helps with performance, especially, for example, selection models, because it becomes much easier to converge them. And especially in the topic of meta-analyses, the p-values are kind of don't really make sense, because to get the proper p-value, you need to know the sampling plan. And when you're conducting a meta-analysis, the studies were already conducted, and there was no sampling plan to perform those studies. So the sampling distribution for specifying the p-value is non-existent, basically. So just a quick illustration was the idea behind Bayesian model averaging. You can imagine that you have here multiple demons. This is from paper about regression. So it was slightly modified, and each demon represents an assumption or a hypothesis about the data. So for example, one demon might scream, the treatment works, the alternative hypothesis is true. There will be another demon that screams, there is no effect, the null hypothesis is true. And then if additional assumptions, we can have our data. For example, there is only sampling variability, there is no additional heterogeneity in the data. So the fixed effect model should be used to describe the data, or there is additional heterogeneity. So we should use random effect models. Or there is no publication bias, which is also an assumption that we make out of the data if we fit either fixed or random effect meta-analysis. And then the last but not least, the assumption that there is a publication bias. So these are 6 different assumptions, or 6 different ways we can specify 3 different ways we can specify the models, binary, either one of those 2. And what we do in Bayesian model averaging, we specify all of these models simultaneously. And then we feed the models, the demons, with the data. And the demons that predicted data the best, so they had the most well calibrated taste for the data, they grow because the data allowed them, because the data fit them well, and the demons are louder. So you can see that, for example, data were aligned with the 3 demons, especially the one about the presence of the effect. So the demon shouts much louder, as well as that there is additional heterogeneity and there is publication bias. But importantly, all the remaining demons still have some weight in what they say, so we don't ignore them at all, but we still listen to them, and we listen to them proportionately. And if you think about it in model types, then if we want to have our model average estimate or our model average ensemble, then we can think about it, we split our prior model probability, which is 1 of the model space, into 2 different models based on the presence or absence of the effect. So on the lines, you see that we split, we put 0.5, put half of the weight to the null hypothesis, null of the weight to the alternative hypothesis. Then we split again equally against model assuming presence or absence of heterogeneity, which would correspond to Bayesian model average meta-analysis that our lab published earlier. And then what we do, we can split the probability again according to the assumptions of publication bias, and that would then correspond to robust Bayesian meta-analysis. So I talked about publication bias and the different methods, but I showed only one demon. So the demon that shouts everything is biased. But how do we deal with the different publication bias adjustment methods? Well, you can imagine that the demon that corresponds to the publication bias, that everything is biased, is just a set of other demons. So it's demons all the way down. And then the other demons correspond, for example, to the PED model, or to different assumptions about the relationship of publication bias, standard errors, or the p-values, directionality, two-sidedness, etc., etc. And to avoid the evidence in the Bayesian settings, we use Bayes factors. So if you've never heard about them, then Bayes factors basically quantify how likely are the data under the compared models. So this is just a definition of Bayes factor. You look at the probability of data under the alternative hypothesis versus my hypothesis if you have 2 models. And if the Bayes factor is larger than 1, then you have evidence for the alternative hypothesis. If the Bayes factor is lower than 1, then we have evidence for the null hypothesis. Because it's a ratio, then you can reverse it and you get the evidence for null hypothesis in favor against alternative hypothesis if you just switch p data h1 divided by p data h2 to the power of -1. One nice identity that we use if a multiple models is that also Bayes factor equals the change from prior to posterior odds. And if you have multiple models, we can use this equality and specify so-called inclusion Bayes factors. So basically, we just sum across the primary probabilities of models assuming presence of something versus models assuming absence of something. So here, A and B define two sets of models, and how we define the sets of the models over which we sum defines the hypothesis test that we specify. So for example, if I change letters. So for example, here now we have I and J instead of A and B. If I corresponds to all models that assume that there is presence of the effect, and J to all models that assume absence of the effect, then we can inclusion-based factor for presence of the effect. And similarly, we can define inclusion-based factors for heterogeneity, publication bias, etc. So this is a very general formula that can be used for specifying base factors on multiple models. To get posterior estimates, we just combine the different posteriors from the individual models and weigh them by their posterior model probability. So here, if we just look at two different models, for example, fixed effect model and random effect model in orange and green, then we can just weigh them by their posterior model probabilities, and we get the average posterior distribution. And if we have multiple models, we just average across all of them. And in RoBMA, we also average across models assuming absence of the effect. So then there's also point density at 0, and we have mixture distribution as our posterior distribution. So the publication bias adjustment components that we use in RoBMA contain the PET and piece models that correspond to the models that assume there's some relation between effect size and standard errors. And then we also specify 6 different weight functions that look at different assumptions about 2 or 1 state selection on significant or marginal significant p-values, and whether there's also effect of the direction of the effect or not. Which basically covers all these models from the selection. We don't cover trim and fill because it imputes studies, so you can't really compare the marginal likelihoods. And we don't use endogenous scaling because we saw the paper only too late when we were developing our previous paper. So how does it perform on the current example? If you just look back, in some cases, it performs as well as either PET piece or 3PSM. In some cases, it performs better than either PET piece or 3PSM. So the important thing is there are more models than only those two. And also we are averaging across models assuming absence of the effect. So you can get estimates very close to 0. But also in some other cases, it performs worse than one of those models. So if you look across all of them, you will see that the green estimates are on average closer to the blue ones than the remaining ones, but it's still statistics, and you can see that we can also get the wrong results in some cases. If you just look at the results numerically, then if we look at the comparison of the RoBMA and the PET piece and 3PSM, you see that in terms of bias and RMSE, there's quite some improvement as well in overestimation factor. And also we have a lower amount of false positive rate and false negative rate. Although there's a lot of undecided results when we use RoBMA, so it's really hard to tell whether it's an error or not. So this was some very short background on RoBMA and how it works. So and I will show how we extend it to meta-regression. And yeah, so how we extend to meta-regression? Well, RoBMA Bayesian meta-regression basically just tries to extend RoBMA to moderator analysis because moderators are very often used in the meta-analysis, and it's important to study them. And before, it was basically impossible to deal with moderators apart than splitting the sample, which have some undesirable properties. So now in the robust Bayesian meta-regression, it allows us basically the whole extension, just allows us to do Bayesian model averaging and to use multiple models simultaneously. And those additional models will be the models changing with respect to the moderators. And then the extension just allows us to do the same things as before, but we don't only need to account for the uncertainty about the presence or absence of the effect, heterogeneity, or publication bias, but also about the absence or present moderators. And that means that also when we draw inference about the effect, heterogeneity, or publication bias, we also adjust for the moderators and vice versa. So when we are estimating the moderators, we also adjust for the uncertainty the remaining model components. And then we also can quantify the evidence for the presence or absence of moderators. And both of these things are especially important, I would say, in meta-analysis, because if we look in the previous models, then even in the simple meta-analysis, there is a lot of uncertainty in the model structure. So, and when we can either select pet piece or selection models, then adding moderators to both of these methods will just add more uncertainty, and it creates just more different models that we have to choose from. So this just ties back the whole possibility of choices into one model average inference. And the second thing that in moderation analyses, there is usually very low power to test for the presence of the moderators, and then it's impossible to tell whether there is absence of evidence or evidence of absence again. So if we have Bayes factors and we can test for the presence or absence of the effect, or we can summarize that we have not enough evidence to say whether the moderators matter or not, and we still need to look for more additional studies. So how does this work conceptually with the moderators? Well, I can now finally use the original slide from the regression without adding additional notation. And we can either include, if you have multiple predictors, we can think that we can either use one predictor, or we can include all predictors, or maybe we should include no predictor. So there are also differences in structure based on which predictors we include into the model. And then we just tied with the rest of our Bayesian model average ensemble by splitting the models with the different types of moderator structure according to the presence or absence of publication bias, heterogeneity, and the overall effect. And then and there's publication bias, then the different types of publication bias. So we just add one more layer to the whole model ensemble by specifying the different types of models with moderators. If you think about back how we evaluate the evidence for the presence of moderators, we just use, again, the inclusion Bayes factor formulation. So here, oh, my monitor is turning off, sorry. So here again, we just use the inclusion Bayes factors, and instead of defining them to either get evidence for or against the effect, heterogeneity, or publication bias, we specify a set of models that either include a given moderator or exclude a given moderator, and then we get inclusion Bayes factors for a given moderator. And we can do this for all of the moderators, averaging across the models with different model structures with respect to the presence of the overall effect, heterogeneity, publication bias, and all the other moderators. And the very same thing again with estimating parameters under meta-regression. So we again can get posterior distributions for each individual parameter, averaging across all of the models and weighting them by their posterior model probabilities. So the whole idea is basically very simple, and you might ask, is it even worth writing the paper about this? Because you just add one more structure to the model at predictors. Well, there are some complications when you talk about moderators, especially in Bayesian settings. And one of them is parameterization, and the second one is follow-up analyses. So I think these are two things that are slightly difficult to correct for this paper, especially in meta-analyses. And let's start with the parameterization. So in meta-regression, you can have two types of moderators, either continuous or categorical. And the type of moderator, especially in Bayesian settings, or how you treat them, makes a lot of difference for the hypothesis test and for the estimates that you obtain. So, for example, the different scaling, if you have continuous moderators and different contrast codings, corresponds to different hypothesis tests. And if you start with a simple case with the continuous moderators, if you center your moderator, then the intercept in the model, in the meta-regression, then corresponds to the mean effect, which is, I would say, very good in most cases, because then the prior distribution on the intercept then corresponds to the effect in the usual meta-analysis. So you have a very nice comparison between the parameters and also the hypotheses. If you don't center, then your hypothesis test for the intercept and the prior specification becomes very odd. So this is one thing that needs to be taken into account. The second thing is scaling. And in Bayesian settings, there is a difference whether you put a predictor on a scale of kilograms, grams, or milligrams, because the predictor will have different ranges, and the way how you define prior distribution is affected by the scaling of the predictor. So what you should do, or what's usually done in Bayesian analysis, is the standardization of the predictor, and that allows you to have scale-free regression coefficients. So then the prior distribution is independent of the scale, is scale invariant with respect to the predictor. In categorical moderators, it becomes slightly more complex, and that's because if you use dynamic coding in Bayesian settings, then the default category then corresponds to the intercept. So your specified prior distribution then corresponds to the effect in the default category, and also the test for presence of the effect, if you would just use this parameterization, would correspond to the test of the effect in the default category. And then the individual coefficients of the additional categories are then tests for differences between default and remaining categories. The way how this is usually treated in Bayesian settings, for example, ANOVA, if you have categorical moderators multiple levels, you use so-called scaled you can usually use sorry, I cannot pronounce this ever. You use orthonormal contrasts, and these contrasts ascertain that your intercept corresponds to the mean effect, and then you have n coefficients for each of the levels, and these are regularized that they sum to 0, and those different coefficients correspond. These coefficients correspond to the difference of each category from the mean effect, which nicely allows you to specify prior distributions on the differences from the grand mean for each category of each level of the category, which also means that the factor becomes the moderator that has categories becomes label invariant. So it doesn't matter what category is which I would say in most cases for testing whether there's moderation, for example, by nationality or by sex or some other categorical moderator where there's no default category that you want to set as a default and then test for difference from this, might be a preferable option. And then when you have your parameterization, then you need to have set some prior distributions, which is always a place of contention, especially in your Bayesian, because first of all, Bayesians disagree on all things, but especially prior distributions, and there are no two Bayesians that would agree on the prior distribution of another Bayesian. So here is our proposal that what we deemed as kind of reasonable prior distributions for the different type of predictors when we use coincidences as our dependent variable. And I would just take this as a suggestion which you can use when you analyze data. And of course, you can specify different prior distributions, and I will show how in the package. And I think the major philosophical point is specify different prior distributions. You are basically specifying different hypotheses. So if you specify very different prior distributions, you are specifying different hypotheses. You have different questions. Different questions will lead to different answers. But if you specify similar prior distributions, which I think most people would, then you are asking very similar questions. And if you're asking very similar questions, you should get similar answers. And if you get very different answers from very similar questions, then maybe the problem is with the data, and you need to collect more data and check some other assumptions, and the problem is not in the priors themselves. So speaking of the priors for the mean effect size, we think that the standard normal prior distribution works quite well. That's what we were been using before, and we tested in multiple simulations. It does seem to have quite a good performance. And for moderators, we think that the moderators usually have much more effect than that's the grand mean. So the differences between the different levels are probably going to be smaller than the average effect size. So we think that 1/4 of the standard deviation will be probably a good specification for small effect sizes and small differences between the moderators. And similarly, for the orthonormal contrast, when we just look for difference from each category from the grand mean, then we again set 1/4 as a default. And that's one this specification that I will use for the rest of the examples. The second problem that you encounter in meta-analysis is testing for subgroup effects. So one thing that you usually want to do is not you want to test whether there's a difference between the moderators, but if you just look at the moderator of a level of some moderator, is there an effect in this group? So you want to test, does the effect differ? Like, is there an effect in this category? And in frequentist way, you would usually just use marginal means. Now it works quite well with metaphor, and you can just fit your model and get the marginal mean estimates and test them against 0, for example. The other option would be to do, or like, okay, so I step ahead. The first usual option would be that you do subgroup analysis when you subset the data, which I think is suboptimal because you're looking on the part of the data. So your estimates of heterogeneity or publication bias or other components are just based on the small subsample. Also, if you have additional predators, it might be much harder to estimate them. And but in Bayesian setting, we cannot really do, like, it's much harder to get a test for difference from 0 for different individual levels, because you need to specify a prior distribution on your parameter to get your hypothesis test. But we want to specify prior distributions on our overall model parameters, which is the grand mean, and then the differences from it. However, what we can do, we can look at the implied prior and posterior distributions on the differences from 0 for each of the coefficients. And here we use another trick, which is called Savage-Dickey density ratio. And it allows us to look at the base factor, again, in a different way. So if we are looking at nested hypothesis, so including or excluding one parameter, here it would be that the parameter is unequal to 0. So our compounded parameter, which is sum of the grand mean effect plus the difference from the grand mean for a given category, is equal to 0. We can use this formulation, which looks at the prior density, assuming there is either effect or moderation, and the posterior density of whether there's either effect or moderation. And then we can look at the change from the prior density to the posterior density, and this allows us to get us our base factor. So this addition then allows us to test for the moderation for the differences from 0 for each individual levels. And I will also show it on an example when we get the base factors. So we can realize one data set that we already analyzed before, and this is no evidence for nudging from the very famous nudging meta-analysis in PNAS, where basically the original authors concluded that choice architecture is an effective and widely applicable behavior tool change. And it's working across all different settings, moderators, etc. And then us and additional 2 or 3 teams wrote a commentary showing that there's a lot of publication bias and there's no overall effect. And there's also a lot of heterogeneity. So it's very hard to roll. So there we found no evidence for the overall effect, and we also found evidence against some different moderators when we did subgroup analysis, and other teams also found absence of evidence for the effect. But now we finally have the moderation analysis, so we can analyze the data all together and look at the moderation without actually doing the subsetting. So let's quickly do that. This is the funnel plot from the original studies, and we can see there's probably a lot of publication bias. And if you analyze it with RoBMA, then we get the 3 main components, which is the overall meta-analytic effect size, which is the unweighted average of all studies, and then the heterogeneity. Here we see that we get base factor of around 1.2, which is absence of evidence for either the effect or for either the presence or absence of the effect, and the meta-analytic estimate is very close to 0. There's a lot of heterogeneity, even after adjusting for moderators. There's a huge amount of evidence for publication bias. And when we look at the moderation, when we look at both moderators simultaneously, we find evidence for moderation by domain. But we found very little evidence for moderation by domain. but we find a lot of evidence for moderation by category. And if you look at the particular estimates in the category, and this is the model average estimates across all categories, then we find evidence for absence of the effect in the information category, evidence, lots of evidence for the difference from zero in the structure category, and evidence against the presence of the effect in the assistant category. And you see infinity here in two places because the base factors are so large that it's very hard to numerically approximate them. So they are, in one case, they are larger than the numerical precision of R, and the other case, it's just so high that there's no overlap between the posterior density and zero, which you can see here when you have the posterior estimates of those moderators. And you can see that the structural posterior distribution, which is in blue, has is a bimodal distribution, which is a result of averaging across multiple different models, and those models still having kind of substantial posterior probability. So if we choose any of those models, you would have a different estimate, and then the averaging allows us to look at the estimate across all of the models. And then we have the intercept at zero and the change from the prior distribution, which are the dotted lines, and the posterior distribution allows us to compute the base factors that we got there. And this just nicely extends the previous findings, which are now on the right that you see, where when we did just the subset of the data to analyze the different categories, and you see that we got basically the same base factor for if you look across all data. And but now we get much more. If you just look at the intervention category, we get much more evidence for the presence of the null. Here the base factors are reversed, so this is not base factor 0, 1, 0, but base factor 0, 1. So this is evidence of absence. So this is around 0.03. So this is 0.08. So that's very close. But now we find a lot of evidence for presence of the effect in the structure category domain, which before we found lack of evidence for either for and against when we looked only for the subset. So we get a bit more nuanced results that we got before, even though our effect size estimate is still very similar that we had before. And similar for the assistants, before we had our base factor of for the alternate hypothesis was around 0.11. Now it's 0.09. So again, very similar results if you take 1 over 9. So I will quickly overview simulation study. We did just a small simulation study to look how the method performs across different scenarios. This is no way exhaustive, and this is definitely not a comprehensive test how the method works, but we can look at different settings that we might seem plausible and see whether it performs how we would expect. So we looked across different types of different sizes of the true effect moderation. So we had zero effect, small, and a medium effect. And then we had the heterogeneity, number of studies, either 30 or 100, and the publication bias that we simulated via selection models. So there was two-sided selection, and there was either no bias. All studies were published. Marginally significant studies were published half as likely as the significant, and the non-significant were published only with probability 0.2, or non-significant studies were not published at all. And if you look at the results, I will just show three quick tables. So first table look on settings when there is no effect, no moderation, no publication bias, and no heterogeneity. So this would be absolute nothing data set. And in the first row, we have the overall grand mean effect size estimate. Here, all of the methods show that there is no effect, which is good, or the effect size estimates go to 0. Then we look for the test for the presence of the effect, for the overall average effect, and we see that the gray bars are absence of evidence, the black bars or the very dark brown bars is presence of the effect, and the white bars that are only in the Bayesian methods are evidence for the absence. So while the frequentist methods have 5% error rate, in Bayesian settings we even find around 95% cases we find evidence for absence. And for the moderation, if we look here, then the moderator estimates are again very precise for all the methods, and again 5% error rate as you would expect in the frequentist methods, and here we have around 50% power to detect absence of evidence when we use threshold of base factor 10 for making a decision to compare it. So that would be probably more stringent criterion than the p-value of 0.05. If you look at two more categories that are a bit more exciting, I would say, then we have category when there's presence of the effect, presence of moderation, presence of small heterogeneity, and no publication bias. And then we have category, we have simulation when there is effect, moderation, heterogeneity, and there is also moderate publication bias. So if you look at the effect size estimates, there is small downwards bias in the RoBMA meta-regression. So here, sorry, I didn't say that all of these methods are the meta-regression versions of random effect meta-analysis, 3PSM meta-regression, PET-piece meta-regression, BMA meta-regression, and RoBMA meta-regression. So the difference between BMA meta-regression and RoBMA meta-regression is that RoBMA meta-regression also adjusts for publication bias, whereas BMA meta-regression would not adjust for publication bias. So you see, when there's no publication bias, the BMA meta-regression does slightly better than RoBMA because it doesn't have those models that assume there is presence of the publication bias. So if we don't have enough data to completely rule them out, there is still some averaging downwards. But when there is publication bias, then the overall effect size estimate is overestimated in both random effect meta-analysis and Bayesian model average meta-regression. All of them find the presence of the overall effect, which is there, and there is moderate effect, even if there is absence or some presence of publication bias, so that's all good. And then the moderator estimates in the absence of publication bias are well estimated by all methods. We have slightly higher spread in the Bayesian methods here. And if you look in the presence of publication bias, then here it seems like that the 3PSM model that is exactly specified as the simulation process does slightly better than our RoBMA robust Bayesian meta-regression analysis. And then we look at the evidence for the moderation, which is present in both of these cases. We said the frequentist methods have slightly larger power than the Bayesian methods, probably because the threshold on base factor 10 is more stringent than P05. If we look across all of the settings that we have and all of the simulations, then if you look at the moderation effect size estimate here, which is on the left, and look at the root mean square error, then we find that the Bayesian methods, as usual, have usually lower root mean square error. And here, the reduction, especially in RoBMA, is much larger. And the same is true for the effect size estimate across all studies. So while here 1 point is the root mean square error in one of the simulation conditions. So I will finish in 2 minutes, and just how to run RoBMA. Behind the daemon slide, that slide that I didn't present here, because for me it's 7 p.m. I don't want to get into math. So you can see this is all the Bayesian machinery that you need to do to specify the models, update the models, draw inference, etc. And this is the researcher that needs to estimate those models based on this slide. He is not very happy. So what we do, we implemented the package in R. For normal Bayesian meta-analysis, we also have just implementation. That's just click and point interface. And in R, you just load the package and you use specification as you would do in any meta-analytic software to fit here classical Bayesian meta-analysis, robust Bayesian meta-analysis, just with effect, heterogeneous publication bias. And then you get nice summaries that tell you about the models you specify, the primary probabilities, posterior probabilities, inclusion base factors for different components, and the posterior estimates for different parameters. You have some nice plotting function for the effect size. You can do them in ggplot. You can do different parameters. You can look on conditional posterior distributions, assuming there's presence of the parameter, etc., etc. And importantly, you can also specify different prior distributions. So if you want to test one-sided hypothesis of a small effect, you can change also the location and standard deviation of the prior distribution for the effect, or specify only different type of publication bias adjustment if you don't want to specify selections model for some reason. Or here in the meta-regression, you can also just specify meta-regression as you would do with using the formal notation. Here, for example, we have a different example when we have measure and age as our predictors. And then the summary output also includes information about the meta-regressors. So for example, here for the measurement and age, you see that altogether we have 144 models prior probability, posterior probabilities of the different components and the inclusion-based factors, then with different estimates for the different levels and different covariates. And again, you can modify the prior distributions for the different predictors. You can specify different contrast coding, etc., etc. So I think this is a very nice thing about the package, that you can fully modify this model specification and you can play around with it. So to wrap up, advantages of the methodology, I would say that you can incorporate uncertainty about different models with Bayesian model averaging. You can provide evidence for either null or all alternative hypotheses. It has usually better performance in small sample sizes when there is a lot of uncertainty about the models which should be selected. And you can incorporate expert knowledge. And as well, you can do sequential update of evidence regardless of your sampling plan. However, the methods are very slow, and especially in the case of meta-regression, now you have to fit all the combinations of different models, which can grow very quickly. If you have, I think I can do 4 or 5 predictors simultaneously on my computer overnight. If it's more, it becomes computationally infeasible, but we are working on some updates for that. And then in our simulation studies, especially in previous papers, we have shown that RoBMA fails if there is not only publication bias and also strong p-hacking. And especially if there is p-hacking, then this method seems to underestimate the true effect size. So if there is also p-hacking, then you will get underestimated estimates. And often, if there is no effect in the population and there is publication bias and p-hacking, you might often observe negative estimates from your publication bias adjustment. So I will thank you for attention here. There's a link to the package, and just if you want to try the click and point version, this is my favorite cat meme. And if you want to learn more about the methodology, there's links to some of the papers and our latest preprint with deals with the meta-regression. Thank you very much.
Thank you, František. And we've got a couple minutes for questions and discussion. Feel free to post your questions in the chat or use the raise hand feature on Zoom, and we'll call on you.
I see one question in the chat already, and that's 2 questions, and that's whether does RoBMA correct for dependencies and effect sizes. This is an excellent question, and another paper that we are working on. The problem is you cannot get exact likelihoods for selection models with multiple levels, or like you can get them unless there's multiple studies in dependency to get 3-level models, because then you need to compute too many integrals to be computationally feasible. So we are looking in some ways how you discount the data or how you do some approximate 3-level structures. And we have something working, but we haven't run simulation studies on it yet. So hopefully maybe next year sometime we will post a preprint with that. What you can do in the meantime is you can do kind of subsampling when you, for example, select only one study for a given cluster and run multiple times. This reduces the power, but deals with the dependency. And it's not the best solution, to be fair. And then the second question was, is a 50-50 prior always a good starting point for estimating the amount of evidence in favor of an effect, especially if the literature of many studies showing evidence in favor of the alternative hypothesis? Well, I would respond in 2 ways. The first one is that you shouldn't use the studies that you have to specify the prior distributions for your test, because the prior distribution by definition is what you specify or what you think before you observed any data. The second thing is if you use inclusion-based factors, then for the given inclusion-based factor, for example, for the inclusion-based factor of the on the effect, it doesn't matter what's your prior inclusion odds, because the base factor is the updating factor from prior to posterior odds. So if you specify lower prior odds, you will have lower posterior odds. The base factor stands the same. So that's why base factor is very commonly used in Bayesian hypothesis testing instead of posterior model probabilities or posterior inclusion odds, because it's independent of the prior odds. It's again a prior distribution, so not like all Bayesians will disagree with the specification of what I will say, but I think the half-half prior inclusion odds is the commonly used structure across multiple settings, either for regression or different applications of Bayesian model averaging. I think it seems to perform quite well. And if you have different a priori expectation before collecting the studies, you can definitely specify different prior inclusion odds. And the package also allows for setting different prior odds and prior model probabilities for different components. So it's definitely possible to modify it and do different specification.
See David with his hand up. David, do you want to unmute?
Yes, thank you. Thank you. I really enjoy the talk. I'm a big fan of Bayesian methods, but I have a psychological problem. I'm schizophrenic. On the one hand, I can see the advantage of trying to pick simple models by choosing, let's say, but in the simplest case, between mu equals 0 and mu is not equal 0. And if it's not, then I estimate it. But on the other hand, as a Bayesian, I don't want to assume that a particular point value has a positive probability. I want to assume a smooth distribution over possible parameter values and just look at the posterior distribution of it. So it seems, so I don't want to fall into a trap of being like a classical or frequentist of testing a hypothesis. How do you resolve this problem yourself?
Yeah, so I think this again depends on the application, and I can see different settings and different scenarios. For example, I think probably the most famous example would be a nasal oxytocin for improving happiness or bonding experiments. And there is, I think, very plausible hypothesis that there is absolutely no effect of nasal oxytocin on improving bonding, especially because, as been shown recently, I think oxytocin cannot pass the nasal barrier into the bloodstream, so it's physiologically impossible to actually do anything in that. And in that case, I think the null point hypothesis is extremely justified, because then the assumption there is no effect might actually be true. And then I would say you want to specify a positive probability for a given value, which is 0 in this case. And I think there might be many cases where there's actually no effect in the literature and the null are very close to null, so then the null value is good approximation. You can, of course, disagree with it, and many people do. And then you can specify some smooth prior distribution that also for the null or alternative hypothesis. So you can specify so-called perennial hypothesis or interval hypothesis, where you would assume that values in some range correspond to the null, and values that are larger correspond to the alternative. And the package actually allows you to do that. So you can not only specify the alternative hypothesis, but also the null hypothesis. So that would be one way around. The second thing is, if you are absolutely against hypothesis testing, even in the Bayesian way, you can still just remove all of the models assuming absence of the effect, and you can estimate the models assuming presence of the effect. But then all the estimates, I would say, that you obtain are conditional on the assumption that there is a presence of the effect. And if you think that the assumption is implausible, you can do that. But I would say if the assumption is implausible, then the data should tell us that as well. So if the data show that there is evidence against the absence of the effect against the point null, then you should observe a huge base factor for the alternative hypothesis. That would be your continuous distribution. So there are multiple ways how you can approach this, and you can definitely ignore the null hypothesis if you really wish to. Although I myself, I'm a fan of hypothesis testing with the point prior distributions as well.
Thank you. I think the only case, probably the only case I would accept the null as being plausible is ESP, but maybe there's some other ones.
Yeah, that's definitely one of the best examples for the point nulls.
So we are right at time. Thank you all for logging on. We'll be back with one more talk on December 8th, I think it is. Katie Fitzgerald is going to be sharing some new work. So thank you once again to our speaker, František, for a great talk. I look forward to seeing more about what you're up to here. And thanks again for coming.